Recording, okay. All right, this shouldn't take too long since you guys are all familiar with it. I'll just point out any possible changes. One major change is Cengage Unlimited is required. Okay. So you can get the electronic book. I mean, it comes with Cengage Unlimited. And if you want a hard copy rental, you just pay them $8 and they send you one. Right, but you've already got a copy, don't you? Everybody's got a copy of the textbook, don't you?
No, I use the online version.
Yeah.
Oh, that's fine.
I hadn't bought it yet because last semester we had it, but then we didn't ever really use it. And so I was like, I'll just kind of wait and see how it goes.
Yeah, the only reason I'm requiring it this time is because I've got OWL as a homework assignment. Okay, so you go into OWL and there are assignments there, and I'll talk about that a little more in a minute. I'm sure everybody's got a calculator. Let's see. Okay. We're still going to have regular exams, but now the exams only count 69% rather than, what is it, 89? Because the homework counts 20%. And you do homework through Cengage OWL. There's an appendix at the back if you haven't already got an OWL account. And let me pull this out. On this part, Appendix 1, if you go to this address, in fact, in Blackboard, there's a link to it. So if you go into Blackboard and you click on the Cengage link, it'll take you to this place. And you can log in there if you've already got a Cengage account, or it'll ask you to use the code that you get when you buy Cengage Unlimited. Okay. And then when you do the homework, you should be able to go into Blackboard and click on the homework link, which is probably the same one. And when that takes you to that destination, then maybe all you have to do is just log in, and then you have access to the homeworks. And I've got screen captures here to show you, try to keep you on track with what you expect to see when you do the homework. There are two things, there are only two things in the homework that are graded for each chapter. One is what's called the mastery, do that one first. And then the EOC, or end of chapter problems, do that one second. Those are graded by Cengage, and they give me the results. So I don't actually see what you're doing because they got it to where it randomizes. Okay. Now, when you do work the homework problems, you have several attempts available. So if you get it wrong, it'll give you a hint or an explanation of what you did wrong, and try it again. Remember last semester I handed out work problems that you take home with you and all that stuff, and I had printed out massive amounts of paper. Those are still there in Blackboard. Okay, so they're available. It's just that this, I think, is what do they call interactive, and hopefully it'll help you more. But you can still work the homework problems, and they might be of some value, right? I mean, if you work the hard copy type that similar to the ones I gave you last semester. Okay. Okay, let's go to the schedule. All right. The first exam is going to be on chapter 10 and 11. So I had to squeeze 2 chapters into that one. And when we get down also to acids and bases, chapter 14 and 15, are both chapters on acids and bases, so I squeezed those together for one exam. The rest of them are one chapter, one exam. And since September 2nd is a holiday, we skipped that week, so that gives you an extra week to figure out how to do the homework and get it in on time, because there's no late homework. And you've got till midnight on the day of the exam to get your homework in. Anything past that is 0. Because if you haven't done it by then, it's not going to do you any good anyway. Let's see. Okay, so we're going to see if there's anything different in here besides that. Everything else is the same as last semester. Let's see. Zoom, everybody knows.
Lab every Monday.
No, not every Monday.
So are we skipping like a Monday? Like we'll have
Basically.
like if we just have a lab today, we wouldn't have a lab next Monday.
I don't want to say for sure. We'll talk about the lab. What I'll do is I'll run through chapter 10, then we'll stop and do lab. We don't have a lab today, of course. So, and then once we get that out of the way, then we'll go into chapter 11 and finish it up. Everybody knows about Zoom, how to get into Zoom. Okay, so if you're absent and you want to be counted present, you just zoom in and stay in. Don't zoom and leave. And then you get counted present. If you happen to be, now that's in a Blackboard, right? Everybody knows how to get into it through Blackboard. But if you find yourself out, you don't have access to Blackboard, but you are connected, then in Appendix 2, the #1 item gives you the meeting ID. It's the same ID for every class. You just log into newriver.zoom.us, right? And you have to have the Zoom app on your device, whatever your device happens to be, laptop, tablet, phone. Then you can open that up and join the meeting at that number, 276-621-334. And you can join it from anywhere you are, as long as you're connected. I didn't know that I could have done it last semester, but I didn't realize that you could do it that way. The other thing is, I have a syllabus agreement. So the last page of your syllabus is just sign, print your name, date it, just to say that you received it. I'll keep that for records. Just do that sometime before you leave today. All right, get that out of the way. And we'll jump into chapter 10. All right, chapter 10, liquids and solids. Let's see. Yep, it's recording, that's good. Oh, by the way, when you go into Blackboard, if you want to review the videos that I record for each of our classes, all of the videos from my 102 last semester are there. Right? So if you want to jump ahead, you'll see me teaching a different class. But what I'll do is, as we generate these new ones, I'll replace yours with these, or add them there, so you can see both of them if you want. Okay, yeah, everything's there. So terminology, let's define some terms. the difference between inter and intra. Right? Intra means inside the molecule, in this case. Intramolecular bonds are those bonds that hold the molecule together. Intermolecular are the forces that molecules experience when they come close to one another. And in order to form a molecule, you need covalent bonds. You have to share electrons. Because only the molecules that, well, only molecules which are formed by covalent bonds are strong enough bonds so that they behave as individual units. Right? Ionic bonds, they're not strong enough. In a solid, of course, they're in sort of a network of positive and negative charges. But in a liquid, if they're soluble in the liquid, they break apart into individual ions. Molecules don't do that. So what kind of forces hold or affect molecules when they come close to one another? If the molecules are polar, that is, we defined polar during the first semester. We didn't do that. I'll refresh your memory. What do we mean by polar? Think of a magnet. Right? Magnet has a north and a south pole. Molecules behave similarly. Not exactly. They're not magnetic poles. They're electrical charge distributions. Right? So if you have a compound that is made of ions, like sodium chloride, that's not valid as a polar molecule, because it's like cutting your magnet in half, right? If you could keep the south away from the north, of course we know if you cut the magnet in half, this becomes north and that becomes south, right? So that's not a perfect example. But in order to be polar, you need a molecular compound that is covalent bonds. Now, if the distribution of electrons between the, let's do this one. Carbon dioxide would be like that. We can speak of polarity in terms of bonds and in terms of molecules. Right? So now, let's focus on the bonds. What is the attraction of each atom for electrons? Right? The attraction of oxygen in this molecule is stronger than carbon. Right? So the electrons want to spend a little more time with oxygen than with carbon. They're still shared, but the electron density is a little higher over here and a little higher over here. Right? We use a symbol like that to show this is the positive end and electrons want to be over here more. So it's a slight redistribution of electrons. And we would be like that for the other side. Okay? So that's the individual bond is that way. So to show a redistribution of charges, we use a symbol called a delta. It's a Greek letter. There's a minus. That's where electrons want to be. Remember, they're still shared, but it's a slight negative charge. And for this side, it's positive. So we got another one over here like that, and we got another one here, so actually there's two of them. So you get this slight electron density redistribution, and if we drew the electron map, it would be something like this. You know, more electron density out here on the ends. So the bond itself is polar. It shows polarity. That is, it shows slightly more negative over here and positive over there. Now that's for the bonds. For the molecule, you sum the polarity of all the bonds. And by summation, I mean vector summation. You understand what that means? No. Physics. the vector summation is what are the components of that up and down. Since it's this way and that way, it's just a straight summation. So this pull that way cancels this pull this way, and the whole molecule is non-polar. Because that negative cancels the other negative, right? It's exactly opposite. And the bonds are identical. Okay? But for something like water, which is shaped like this, right? You get like that. Now, the summation of these bonds are not perfect. They're not opposite one another. So the shape of the molecule determines whether the molecule is polar or not. So if it's slightly negative here, slightly positive there and there, the overall polarity of the molecule is for that end, right? Negative. So that's why water molecules are polar, carbon dioxide molecules are non-polar. You take two things into account. One is polarity of the individual bonds and the shape of the molecule. Questions? Okay, I sort of jumped ahead a little bit there, but a stream of consciousness. Now go back to my slides. Let's see. Have I jumped? I jumped ahead. Okay. So, what kind of effect do individual molecules have on one another when they're together, right? Since these are nonpolar, there are no charge interactions, significant charge interactions, right? No polar versus nonpolar. Whereas water molecules are definitely polar, and they tend to interact, line up so that you have an oxygen here like that. And they form an attraction between this negative and that positive. Now you could make the argument that you could do like that. You get some interaction, and that does occur, but it's much, much, much weaker than this one. Okay? So these are the types of intermolecular forces that you can have. Dipole, dipole, right? This is a dipole, where you have slight redistribution of electron density that gives you not a complete charge, as in an ion, but a slight charge. And you get interactions. And then within that dipole-dipole is this special kind of bond. Water characterizes that, is the hydrogen bond, where you have hydrogen and some other electronegative atom here, some one that draws electrons to itself, makes it negative and hydrogen positive. So that hydrogen bond is on the stronger end of the spectrum of dipole-dipole interactions. Right? That's why water is liquid at our room temperature and pressure. If it were not for these interactions, water would be a gas, just like carbon dioxide is a gas under these circumstances. That's a good thing, right? Because if water were not this way, we'd be in big trouble. We wouldn't have any oceans. Weaker forces than this are London dispersion forces. So what's required for London dispersion? Well, all molecules have London dispersion forces, interactions. It's just that if you have dipole interactions, they swamp out the London dispersion because they're so weak. Right? So it's not like the London dispersion forces disappeared. It's just they're not strong enough to express themselves. But if the dipole interactions are missing, the London dispersions are the only thing left. So when do they occur? And why do they occur? London dispersion forces can be experienced with individual atoms, like the noble gases, or with nonpolar molecules. Those are the ones that you can actually detect the London dispersion forces. So how do they occur? Well, the basic concept that allows London dispersion forces to occur is that electrons are not static. They're in constant motion. So what they tend to do is, over the time frame of picoseconds, it's instantaneous, you get instantaneous redistribution of electron density. Right? So let's take a big, like Krypton. Right? So we've got these electrons out here. I won't draw all of them. And what happens is, over an instant of time, more electron density is over here than there is over here. So that gives you a slight positive here and a slight negative here. It only happens for an instant. But when it happens, any Krypton atoms that are close to it experience a pull on the electrons from this instantaneous positive charge. So you get a collection of electron density over here and just a few over here. Right? So that redistribution gives you a negative here and a positive there. Once you've got that, for that very instant, you get an attraction. That's a London dispersion force. Okay? It comes instantly and it's gone. Now, how do we know that that's a valid or an adequate explanation for what happens? The reason we know that it happens, and it can be measured, is that Krypton is a gas at room temperature, but as you cool it down, slow the molecules down, they have more time to interact. Right? They're moving more slowly. So when they come close to one another, there's more time to interact, and eventually you can turn Krypton into a liquid. Now, what does that say? If it's a liquid, that means there are strong enough forces there to hold it together in the liquid form. And this is the explanation. London dispersion forces allow that liquid to form, rather than cooling it down and it's a gas all the way down to nothing. Of course, that was the assumption from Kelvin. We devised this temperature scale, remember? So that's what hydrogen bonding looks like in water. There we go. And the way molecules line up, right? So if it's in a liquid, there'll be sort of a random arrangement of delta pluses and delta minuses. When we get down close to solid, then they start to line up in a crystal structure. That's why snowflakes have 6 points, because you get the arrangement of the water molecules are such that they form this 6-sided structure. Right? With, let's see, with hydrogen here, oxygen there, oxygen here, hydrogen here. So they form this hexagonal structure, and that's why water, when it turns to solid, ice, is less dense than liquid. Because in order to form this structure, you create an empty space in there. And that's volume. So water, as it freezes, expands, takes up more volume, which means lower density. That's why water, ice, is less dense than water. Okay. Let's see. Phase changes. Anytime a type of phase change that occurs is a physical change. We're not breaking any intramolecular bonds. That is, no bonds are broken within the molecule. You are just changing the interaction of the molecule. So as you cool it down, slow things down, then the molecules have more opportunities to interact. And at some point, you change from gas to liquid and then liquid to solid. That's sort of stylized. Gases have lots of space between the molecules. Liquids, not so much, and solids, a little bit less, most of the time, except for special cases like water. But the trend is generally very low density, much higher density than the gas, and a little bit higher density for the solid. Okay, so that's what's going on. If you go from, okay, this explanation is going the other direction. You start from a solid, you're adding energy, and eventually the energy, and remember when you increase the temperature, what does that mean? Temperature is a measure of average kinetic energy of the molecules. Okay, so the kinetic energy of a molecule, of atoms or molecules in a solid are due primarily to vibration. So you heat them up and they start vibrating. And eventually, they vibrate so vigorously, they break the bonds that hold molecules together. So now they become liquids and they can flow past one another. Then if you go from liquid to gas, you just continue adding energy. You get to the point where you completely break any interactions. There are no interactions to speak of between molecules as you move to a gas. They're free agents. Lots of space between them. They bang into each other every now and then. So these are the densities of gas, liquid, and solid for water. Right? Notice that the solid, or ice, is less dense than the liquid. Maximum density for water. When does that occur? 4 degrees centigrade. So as you go from gas to liquid at 100 degrees, you shrink from this density to something akin to that, a little less dense. And it continues to increase density of the liquid water until 4 degrees. And then at 4 degrees, you start getting some regular interactions. And then the density goes down again until you reach ice, and that's the point at which it's lowest. As you continue to freeze ice below 0 degrees centigrade, the density increases again. It tends to allow them to shrink and become closer and closer and closer. So the density of ice at the bottom of a glacier is pretty high by comparison. Dipole forces. This is the that arrow that I gave you before expresses a what's called a dipole moment, and that just means that that's a fancy word for slight redistribution of electron density. But it can't be measured, okay? So moment is a term in physics that means a measurable force. Right? So you can measure the difference. You can measure this value as a vector force. How it behaves in an electric field, that's a dipole moment.
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds. Therefore, it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
Okay.
Some polar molecules have
More.
unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water with 2 hydrogen atoms and 2 unshared pairs of electrons can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the X structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
Great. Let's see, that doesn't tell us anything new.
In solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
There you go. Okay. Melting and boiling points. So, as in general terms, we're not talking about quantitative, but qualitative. As the intermolecular force strength increases, you also increase the temperature at which the substance melts or turns into a gas. Okay, so those stronger forces, the stronger intermolecular forces, stronger forces mean higher temperatures for melting and boiling points. Okay? The trend. And this just shows the trend. Let's see. Let's see what the Carbon, silicon, germanium, and tin are in this family. So as you go down the family, you increase the boiling point. And since these are nonpolar molecules, right, the only thing that can hold them together is London dispersion forces. So how does that relate to stronger London dispersion forces going from here to here to here to here? Size of the molecule, right? Because silicon is a bigger atom than carbon, and germanium is bigger than silicon, and tin is bigger than germanium. In other words, the larger the molecule, or in this case, the larger the central atom, the easier it is to have an instantaneous redistribution of electron density. Right? Same thing happens with noble gases. So the freezing point of helium is very, very low temperature. Neon, higher temperature, higher, higher, higher. So the bigger the atom, the easier it is to redistribute that electron density on an instantaneous basis and get those London dispersion interactions. So we have a similar thing going on here as you increase the size of the molecule. Now the trend is okay through the third, fourth, and fifth periods, here, 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 all the way up. The problem is when you get to the second period, other intermolecular forces come into play. What we're finding is that with these, what you're seeing is hydrogen bonding is kicking in. Right? So that's why these have much higher boiling points than these groups in here. Because hydrogen bonding is effectively increasing the intermolecular forces. Right? So these anomalies are attributed, all three of them, to hydrogen bonding. Okay, so let's see if we've learned anything. Which molecule between these two is capable of forming stronger intermolecular forces? The nitrogen or the water? Think about their shape and their polarity, possible polarity, right? Water, definitely polar, right? What about nitrogen? That's nonpolar, isn't it? Right? So the stronger forces should be those associated with water. Dipole-dipole interaction, in fact, even stronger than that, hydrogen bonding. So that's the stronger one. What about these two? They're exactly the same molecular formula. C2H6O. But one has the oxygen out here on the end. That's ethanol, right? The drinking kind. And one has oxygen in the middle. That's dimethyl ether, right? So which one is polar? You see, this is symmetrical on either side. So that's got to be nonpolar. Whereas this one has oxygen, hydrogen out here on the end. It looks like half a water molecule. So this one is going to have hydrogen bonding. This one's not. So ethanol should have a much, much higher boiling point than ether. And in fact, it does. Well, I didn't animate this one any. Okay, so what do we mean by ideal behavior in a gas? As you compress the gas and cool the gas, it stays a gas, right? To a very, very low temperature, right? if you compress nitrogen, it doesn't turn to a liquid until you get down to minus 195 degrees centigrade. And this is carbon monoxide, and as you compress it, it freezes at a much higher temperature than nitrogen. So the ideal behavior will be exhibited by the nonpolar molecule, whereas carbon monoxide has a polar structure. Right? It's only got 2 atoms. Oxygen is more electronegative than carbon. So the dipole moment is toward oxygen, and you get a dipole-dipole interaction, which causes it to behave non-ideally. Right? According to the kinetic molecular theory of well, in this case, gases, when 2 molecules bang into each other, what do? If they're ideal, they just hit each other and bounce off like billiard balls. If there's any interaction at all, that contributes to non-ideal behavior because they're attracted, or in some cases repelled. Depends on the direction they approach. So that changes their non-ideal behavior. Nitrogen is the ideal, the more ideal gas, simply because it's nonpolar. Okay, those are gases. Liquids express very low compressibility. Liquids are not incompressible. They can be compressed. In fact, measurements have been made at depths of 1 mile, 2 miles deep in the ocean, and you find that, accounting for other variables like salinity, that the density of water at those depths is much higher than it is at the surface. So liquids can be compressed, but it's very low compressibility. They're not rigid. In other words, they need a container to maintain their shape. They have relatively high density compared to gases. And they have a significant intermolecular interactions that give them what we call surface tension. That is, it's a resistance to the spreading of the liquid. In other words, if you could grab hold of the liquid on one side and the other and try to pull it apart, you could measure a tension between the molecules. Now, these large intermolecular forces, like water would have, give it high surface tension. That's why you can take a needle, if you're very careful, and set it on the surface of water, and it'll suspend there. We know that steel is much denser than water, and it shouldn't sink. But it doesn't if you're careful. And there's some insects that take advantage of that. Water skimmers, they have their legs spread out like that, and they just run across the surface of the water. And you see when you drop something in water and it sits there, you see an indentation. What it's doing is it's gathering the strength of more and more molecules as it dips until the point where they're in equilibrium, the balance. So liquids with large intermolecular forces have very high surface tension. And many of the cleaning products that we use on our clothes and dishes defeat those intermolecular forces. They're called surfactants. In other words, they destroy the surface tension of water. Why? Because otherwise, many fabrics, the water would just flow across the surface and it wouldn't get in there and take the dirt out. So the surfactant breaks the surface tension of water so it can go into the clothes. And then, of course, there are detergents that go along with it and bridge the gap between oils and water. Another evidence for that surface tension is capillary motion. Right? If you have a tube that's this wide and you dip it in a liquid, the liquid's basically going to be right there. But if you have a very narrow tube, the surface tension is high enough so that, and the attraction between the liquid and the glass tube, particularly in the case of water, is high enough so that it pulls itself up to a point where the force that's holding it up is balanced by the force of gravity that's pulling that column down. So this column is so wide, the only force that can hold it up is at the edges, and that's not strong enough, right? But if the tube is narrow, you have, say, the same amount of water in volume, but you have much higher forces because the tube is narrow. That's capillary action. And it's actually a battle between the cohesive and adhesive forces. The cohesive forces are those that hold the liquid together. Right? Adhesive forces are those that attract the liquid to its container, or the capillary tube. So what you're doing is you're balancing the adhesive forces attracting it to the glass tube, the capillary tube, whatever it happens to be made of. Balancing the force, cohesive and the adhesive forces. So once they're balanced, it stops moving up. Now, if it's water and glass, you get that type of meniscus, right? Because the adhesive forces between water and glass are stronger than the cohesive forces between the water molecules. If it's the other way around, if the liquid you put in there, the cohesive forces are stronger than the adhesive forces, you get a convex meniscus, and you see that in the mercury tube, in a glass tube. Okay? It depends on which one wins. That's the shape of the. Most of the time, we conduct experiments in aqueous solution, so you're going to be looking at that one. And glass tubing is calibrated to read the meniscus at the bottom. Now, if you've got a mercury barometer that measures air pressure, that scale is going to be calibrated for the top of the meniscus, because that's taken into account. That meniscus for mercury is taken into account in the calibration. Okay, what are these intermolecular forces? What effect do they have on viscosity? What do we mean by viscosity? A liquid's resistance to flow, right? So if you see, I don't know, volcano in Hawaii erupting, it's got this lava coming out. It flows across the surface of the ground and just kind of moving. You can walk faster than it moves. It's very viscous. Honey is very viscous, particularly if you get it cold. It has a resistance to movement. Those liquids that have large intermolecular forces tend to be highly viscous, right? So what do we attribute those high molecular forces to? Well, the intermolecular forces can be simple, as in dipole-dipole interactions, but they can also be attributed to entanglement. So liquids that are composed of long polymer chains tend to be entangled more. And that means that they resist motion because, you know, it's like, you ever had a ball of twine that you wanted to untangle? It can be difficult. There's a long string and it just gets in there. Or if you have a knot in your hair, or maybe one of your pets has developed a knot. How do you untangle it? Scissors. Right? But the length of that, the entanglement, is what is attributed to many types of viscous materials, right? And that's how we increase the viscosity of some liquids. In high school, I did a project where I wanted to look at protozoans, you know, small one-celled animals like paramecia. You know what paramecia are? No. Euglena? No. Amoeba? You know what an amoeba is? Okay. These little one-celled animals, under a microscope, since your field of view is very small, they go and they're gone. Can't watch them because they're moving too fast. So what I did was I took my culture of these little protozoans and I added a few drops of hydroxymethylcellulose, same kind of stuff that they put in eye drops. And it thickens, makes the medium more viscous, and that way it's more difficult for them to move through it. And that way I could watch them. But the viscosity there is due to that entanglement of long polymers. Solids. We basically have two types of solids, amorphous and crystalline. And the difference between the two is very simple. Crystalline solids have an ordered structure. In other words, if you look at this part of the crystal and you see a regular order over here, you're going to see the same order in the other part of the crystal. Whereas amorphous solids have no order. Their structure is completely disordered. Glass is a good example. Glass is an amorphous solid. In fact, there's one school of thought that says glass is a supercooled liquid. It looks like a solid to me. You can also, that regular structure can be quantified. It's called a unit cell. In other words, the structure itself, and I gave you a couple of handouts, talk about unit cells. This one right here. Okay. That's an example of a unit cell. Okay? And we'll talk about those in more detail in a few minutes. But only crystalline solids can be described in terms of unit cells. Amorphous solids, since there's no regularity to their structure, you cannot describe them that way. Okay, there are three types of cubic unit cells, and we're just going to really, it may seem like we're going to hit this subject really hard, but believe me, we're just skimming the surface. Right? For this one example, a cubic unit cell, which is very common in nature, right? So we're going to hit that one. There are other types in more detail and more mathematical complexity is involved. We could go beyond this. But these are unit cells, and these are three different ways of representing them. There's a unit cell in a ball and stick. Here's a unit cell in a space filling model. Sometimes this helps to show you where everything is and how much of each one is there. And then the lattice structure, which is just more than one unit cell. So we're going to focus on this one. Okay. Let me see. All right, we'll come back to them in a minute. I'll just call your attention. This unit cell, notice that there's nothing in the middle. It's just everything's at the corner, and that's what this shows. Each is at the corner. So, how many, if you take the unit cell and you say, all right, how many atoms does that unit cell represent? Well, add them up. How much of a atom is that? Well, see, if you take that one and duplicate it on this side, and then duplicate it on this side, and then duplicate it on that side, it takes 4 of them to make a half, doesn't it? So that means there should be 8 of these of that size. So that means this is 1/8 of an atom. So 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1/8 is 1. So this unit cell is only 1 atom. Okay? How about this one? This one has 1 in the center. This is a body-centered cubic because the center of it is this 1 atom in the middle. So you still have the 8s here, and then you have 1 whole one in the middle. So how many in the body-centered cube? 2. Right? 1 atom here, 2 atoms here. This one's a face-centered cube, right here, that face there. So how many faces do you have on a cube? When you roll a die, how many? 6, right? You have 6 faces, right? So this is a half of an atom here, and you got 6 of them, right? So what is that, 3? Right, you have 3 atoms there. Then you still have these 1/8s on the corners, so that's another one. So that's 4 atoms. So the simple cubic is 1, the body-centered is 2 atoms, and the face-centered cubic is 4 atoms, represented by the unit cell. Okay? We let that soak.
That's 1b5.
Well, let's look at it again. You got the corners, right? Right. You still have the 8s for the corners, right? So that's 1. There's nothing in the middle.
Oh, there's nothing in the
Right, right. Nothing in the middle. This one's the only one that has one right in the middle. This is face-centered cubic. So these half atoms are touching one another on the inside. There's nothing in between them. Right. So now you have 1, 2, and 4. Okay. How do we know about the spacing in a regular crystalline structure? We use a technique called X-ray diffraction. In other words, what happens when you pass light through a very fine slit? That slit serves as a source. In other words, a source of radiation. So when it hits that slit, it goes, that's called diffraction. Well, the spacing between layers in a crystalline structure behaves similarly. As we impinge X-rays on it, they're small enough wavelength so that they're in the neighborhood of the same size as the spacing between the layers, and we can tell what's the spacing between those layers using the Bragg equation. So this is an integer. It could be 1, 2, 3, 4, whatever. This is the wavelength of the X-ray, right? It has to be in meters. This is the distance between the atoms in the structure. And this is the angle of incidence. In other words, the X-rays are being shot like this, or maybe at a different angle, or a shallower angle. You have to know that in order to make this equation work. So this is what it looks like. So here's a wave coming in, here's a wave coming in. And as it approaches here, there's your angle. There's your angle, which is identical to that one. You don't have to know how they arrived at this stuff. Just know how to use the equation. So I used to use this on clay structures when I was doing research in soils on my PhD. So I would separate the soil and using a complicated process, separate all the clay out of the soil. And the clay is the smallest size fraction. And then you put it on a slide, and as it dries, the clay particles, they're little like flat plates. they settle in like this, and they lay flat, let it dry. So they form these layers like that. So you put them in the machine, and you scan through, with your X-ray, you scan through like that, and the detector measures the intensity. So when the intensity is reinforced, you get a peak out the other side. And that tells you the angle that you use here. And then you can tell what's the distance between the two layers. I'm not sure if your homework has any of those analyses or problem types. I had a couple of them in the hand homework that I used to use. Types of crystalline solids. Okay, you can have ionic solids, right, like sodium chloride, where you have regular spacing of the cations and anions, right? Sodium chloride would just be a cation, anion, surrounded by anions on all sides, and then each of the anions surrounded on all sides by the cation. Molecular solids. That's where each of the members of that crystalline structure are molecules. Okay, for instance, ice. It's a regular crystalline structure of water molecules. Atomic solids, right? Those are made up of just atoms. And most of the time, not always, but most of the time, they involve metals. And they arrange themselves in one of those three forms. You know, the simple cube, body-centered, or face-centered cubic. Most of the time. Examples. Crystalline solids. Okay, diamond, right? Forms itself into a hexagonal pattern. And it's a crystalline structure. If you have a perfect diamond with no flaws in it, theoretically, and shrink yourself down to the size of an atom, you could walk from atom across the bond to the next atom, all the way from one side of the diamond to the other side, without stepping into open space. You'd be always on. The crystalline structure is like a single molecule. Here's an ionic crystalline solid, right? Sodium, chlorine. Okay, looks like it's a simple cubic. And then this one is water. So each one forms a tetrahedron with four other water molecules, but all taken together, they form this regular hexagonal structure. Okay, let's see. If you have an atomic solid, we mentioned that earlier, they can form subgroups, metal atoms bound together by what we call delocalized covalent. Well, actually, they're metal covalents. It's like we don't have to get into a lot of detail here, but the electrons are free to flow from one to the other. And that's what holds them together. And that's why metals are good conductors of electricity, because there's the bonds that hold the electrons in place are fairly weak, and they just give them a little push and there you go. Network solids. These giant molecules. Diamond is one example of a network solid. And then you can form these 8A groups. 8A, what they mean is noble gases. They can be held together as atomic solids. But the forces holding them together are purely London dispersions. How do molecular solids hold together? Well, since they're discrete molecules, they're either dipole, or if the dipoles are absent, London dispersion hold them together. And then, of course, ionic solids are obvious. They're positive, negative charges holding them together. All right. We're probably going to bleed over into lab time anyway. So let me see how much more we've got to cover. A little bit. It gets kind of heavy. People who understand this stuff best are those that are able to visualize in 3 dimensions. I don't do that very well. So my explanation is going to be a bit weak. In fact, women tend to do better because of spatial orientation and multitasking and all that other stuff. It's not that men can't learn to do it. It's just that in general, women do better with 3D stuff. Okay, so what's a model? A model always means that there's a theory behind it. Right? When we form a model, then we're saying we think we know why it happens. So this model, the closest packing model, makes a couple of assumptions. And we're talking about, when we talk about closest packing model, we're talking about metal atoms that form our solid. So we let the other things aside. Now we're talking just about metals as they pack together. So one concept to hold in the back of your mind is that at any given temperature, the way that these metal atoms come together is there for the purpose of minimizing energy. Right? The minimum energy dictates how they pack together. Okay, first assumption. We have to assume that these metal atoms are uniform, hard spheres, like a bunch of billiard balls or gumballs. Or you ever looked at a gumball machine and you see them stacked in there? They stack in there a certain way, right, to minimize their energy. And we have to assume that these spheres are packed in layers. So for instance, this closest packing arrangement is called ABAB. So what do we mean by that? Well, remember the layers. Layer 1 is A. Layer 2 sits on top, but it's shifted enough to where the metal atoms fall into the gaps between. Right? And then we come back in and put A again, because this one's A, the same as that A, simply because they line up with one another, like that. That's why they're A, and why these are B. They line up. So by the time you get past this A, you're into another closest packing arrangement. Another possibility, ABCA. In this arrangement, you got A, B, and C. And C doesn't line up with A, B doesn't line up with A, but by the time you get to A, B, C, and you start again, that one lines up with A below. So this is ABC, ABC, or ABCA for short. Okay. So what is the result of ABA? If we look at the unit cell, this looked to me like ABA produces a face-centered cube, doesn't it? Right? A face-centered cube means that the unit cell represents 4 atoms. So ABA translates into, well, hexagonal closest packing is ABA that forms a face-centered cube as the unit cell. This cubic closest packing is ABCA. And wait a minute, did I see that right? Sure looks like it. Like this unit cell is exactly the same as the other unit cell. Only in this arrangement, it's not hexagonal. ABCA forms the same unit cell. Back up, back up, back up. I never noticed that before. Am I seeing something wrong? Or is there a body centered? No, because there's a face on this one. All right. I don't think that unit cell fits in the one that we've discussed so far. It just doesn't look right, does it? No. This one looks like a face-centered cube. So cubic closest packing for ABCA, that is definitely a face-centered cubic. But the hexagonal doesn't look like it. That's not important right now. I'm not going to hold you to that one. Oh, here we talk about the number of atoms. I jumped ahead. Face-centered cubic is 4 atoms. So, simple cubic is 1 atom. Cubic closest packing is a face-centered cube. That's another term for that one. Face-centered cubic is 4 atoms. Okay, so we can make that comparison. That ABA threw me. I don't know what to do with that one. Okay, what's the length on an edge of a unit cell? Okay, that's what this, I think this one, quantities and queries. So why do we want to know that anyway? Well, if we know the size of the unit cell, the length of an edge, then we can tell what's the radius of the atom. Or if we know what the radius of the atom is, we can tell what the size of the cubic cell is. It works both ways. You don't have to know how we arrive at this, but for this face-centered cubic structure only, if we know the length of the edge, then the radius of the atom times the square root of 8 is equal to the length of that edge. Right? I think those handouts just show you how we arrive at that. Now this is a little more involved. You can actually use the information to calculate the density of silver. If you know that the edge on that face-centered cube is 409 picometers. What's a picometer? And the minus 12 meters. So if it's 409 picometers, it's that many meters. So how do we calculate the density from that? Well, what you have to do is use the face-centered cubic unit cell edge to tell you what's the radius of your atom. And then you use the radius of the atom plus, is it silver? Yeah, silver. Plus silver's mass, atomic mass, Because if you know that the edge is this, what's the volume of that cube? It's that times that times that, isn't it? Right? This, that is the volume of the cube. Length, height, width. Right? So you cube it, that gives you the volume. Right? And the density is equal to mass divided by volume. So you got the volume already. Now you need, what mass does that represent? Well, a face-centered cube is how many atoms? 4. So this represents 4 atoms. Right here, that volume is 4 atoms. What's the mass on 4 atoms? Well, you know that the mass of silver is 107.87. 107.87 grams per mole. But you want to know how many grams per atom, right? Because you got 4 of them. So moles on the bottom. There you go. So that tells you how many grams per atom times 4 atoms. So this would be times 4, and that goes up here, and you got your density, right? Well, excuse me. This is cubic meters, so you need to change that to cubic centimeters. Right? So if this is cubic meters, then how many centimeters in a meter? 100, right? So you just say, oh, another way, excuse me. Centimeters. Cubed. So that gives you cubic centimeters. The reason is the density is generally expressed in grams per cubic centimeter. That's why I'm doing that. So that gives you cubic centimeters, and this gives you the mass of that many atoms in those cubic centimeters. That gives you density. Now, I'm not sure if I worked it out here. No. But that's what it should be. And doing that calculation, you find that 10.5 grams per cubic centimeter is very close to the actual measured density of silver. So that's the other test. If your calculation is close to the measured amount, you know that you're probably on the right track. Okay. Oh, okay. Did we talk about molecular orbitals last? We did, didn't we, at the tail end? Molecular orbital theory? Yeah, we did. Okay. I'm scratching my head. Okay. There are 2 models that are used to describe the bonding of metals. One is the electron C model. That's the older one. But it didn't explain things very well. So the band model for molecular orbitals does a much better job of explaining how metals bond. All right. This is the electron C model, where you have the metal atoms with their electrons scattered all over the place. Right? And they just exchange those electrons, and that exchange accounts for their attraction. But with the molecular orbital, we're talking primarily about valence electrons. Right, so how many valence electrons would be silver? Valence electrons are those that are in that energy level, right? So what's the N number, the primary energy level for silver, right? 1, 2, 3, 4, 5. But remember, in here, you go back 1, because these are d orbitals, right? So this is 4d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, not 12, 13. 11. So you got 11 valence electrons that are in those molecular orbitals. And remember, the molecular orbital theory takes every atom in the chunk and creates molecular orbitals from all of those atoms. So what does that do? Well, if you've got all of those molecular orbitals going in, all of those atomic orbitals going in to make molecular orbitals, the total number of molecular orbitals is huge, right? Because you have to have the same number of molecular orbitals as atomic orbitals that went in to make them. So that means that the energy gap between them is almost nothing. So the electrons are very easily transmitted between molecular orbitals throughout that entire structure. And that interaction of molecular orbitals is what bonds them together. This is another way of looking at it. So here's, if you have a mole of atomic orbitals, you get virtually a continuous collection of molecular orbitals. And they call them bands. Right? So at this point, you've got filled molecular orbitals and these are empties. And notice that the difference in energy between the two is so small, just a little bit of push. That's why metals are such good conductors. Because it doesn't take much energy to move that electron into this molecular orbital, which is able to migrate over to another atom. And it just keeps jumping. In fact, the best conductor of electricity is silver. The best. But we don't use it in our wiring because it's too expensive. Copper's expensive enough. In fact, copper's too expensive to use in long distance transmission. We have to use aluminum. Okay, alloys. What's an alloy? Well, technically speaking, an alloy is a solution of metals, sometimes metals and non-metals. Just mix them together and you make a solution. Of course, you have to do it when it's hot because you can't mix them together when they're solid. There are two types of alloys. One is substitutional alloy. So what happens with the substitutional? You have metals, atoms like that, just for example. And what you do is you substitute some other metal for some of these. That's a substitutional alloy. So it just replaces one of the parent metals with itself. Interstitial alloy is one which has gaps in here, and you put your alloying material in those gaps. That's steel. Iron, substitute carbon in there. It's an interstitial alloy to make steel. Whereas this one would be like, these are copper, and you substitute in here nickel and make brass. Okay. Now, certain types of steel are a combination of interstitial and substitutional alloys. Right? Stainless steel is a good example. If you take iron, originally stainless steel had a little bit of carbon in it, maybe 0.2%. And to make it stainless, we substituted 35% chromium. So chromium replaced the iron atoms, but it still had these interstitial carbons.
In this animation, we will be visualizing the diamond form of carbon. Carbon forms 4 single bonds using sp3 hybridization. Each carbon atom is bonded to 4 nearest neighbors, forming a 3-dimensional lattice. These covalent bonds make carbon in a diamond form a network solid. Network solids are very hard and have high melting points.
Okay, let's see. All right, does anybody need a break? Or are you good to finish this chapter? Finish the chapter, okay. The difference between diamond and graphite. This is a network solid. Actually, graphite is a type of network solid too. But the structure here is each of these units is a tetrahedron. See? 4 spokes off the center. But in graphite, you have a hexagonal in plates. And the only thing holding those plates together are intermolecular forces, weak bonds, London dispersion forces, actually, right? So that's why graphite is often used as a dry lubricant, because those plates slide easily past one another. You can spray them into, we used to spray it into our motorcycle cables as a lubricant, because it wouldn't collect dust. It wasn't a liquid, right? So it wouldn't gunk up your cables. Let's see. The strength of bonds within individual plates of graphite is very strong because you have these unused p electrons that are overlapping and forming this ring structure. And this is the one plate. So the plate itself in carbon graphite is very strongly bound, but not between plates. And that's why. What's a ceramic? I mean, it's basically a fired clay. Very resistant to attack by acids or other chemicals, but it's very brittle. Semiconductors. The basis of our computer technologies, semiconductors. How do you form a semiconductor? Well, you have to start off with a pure substance, and most semiconductors now are made with silicon as the starting material. So if you have pure silicon, then what you do is you substitute in as sort of an alloy. You substitute something on either side of silicon. If you substitute something with more electrons in it than silicon, you produce an N-type semiconductor. It has an extra electron. If you substitute something on the other side that has one fewer electron, then you make a P-type semiconductor. Semiconductor just means it will conduct electricity, but it's not efficient. It conducts when pushed. So with N-type semiconductors, what moves when you apply a current or apply a voltage? What moves is the extra electron. Okay? What moves with a P-type semiconductor? Well, this is a conceptual thing. What moves is the hole. You're missing an electron, and they call that a hole. So the hole moves around. Don't ask me. It just, I guess it makes conceptual semiconductors easier to handle. All right.
Water is a molecule made from non-metal elements. In the solid phase, these covalently bonded molecules are attracted by weaker dispersion forces. Long-range order exists between molecules that have irregular formation. Molecular solids are relatively soft and have low melting points. Crystallized water occurs in many interesting forms, including snowflakes.
Sodium chloride is typical of ionic solids. The crystal contains alternating sodium cations and chloride anions packed in a three-dimensional array. Ionic solids are brittle if deformed and will fracture along planes of packed ions.
Okay, so up to this point, we've been talking about, we had discussion about metallic solids, right, and the way they pack together. Now we're moving into the other two, the molecular solids and the ionic solids. So the ionic solids are reasonably stable, high melting point substances. And the electrostatic forces, now the bonds between individual ions are weaker than the molecular covalent bonds. But if you add them all together for the whole crystal, they exhibit considerable strength. So that's why the attractions there establish for the ionic solids very high melting points. Right? You're talking about, I don't know what it is for sodium chloride, but it's like 1,800, 2,000 degrees centigrade. Very high. So the ionic solids, you know, here's the hole, you know, for the layer above it to fit into. This is one type for closest packing structures. And in this case, the hole tends to form a tetrahedral structure, right? If you consider what's left, the space inside is the center, then you've got one here and you've got three there. So you have a tetrahedral arrangement. Then if you take these three and you put them together so that their bulges fit into the holes, you end up with an octahedral arrangement. So octahedron means what? 8 sides? So let's see if there are 8 sides. There's one here and there's one on top. So that's 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Well, that's only 6 sides. 1, 2, 4, 5, 6. Oh, 7, 8. Okay. So on the front side, you got this one, 2, 3, and on the back side, you got that one, 1, 2, 3. Then these two. So that is 8 sides. So you do have an octahedron there. So depending on the size of those holes, if you increase the size of the holes, then you go from trigonal to tetrahedral to octahedral. So the bigger the hole, the more complex, right? So only 3 together here for this very small spacing. If you got a bigger size hole in there, you get tetrahedral, and bigger still, you get octahedral for ionic solids. That's straight out of your book. It just gives you characteristics of each one. This is where I wanted to get to. This is a little bit easier to understand. So if you put a liquid in an enclosed container, and it can either be evacuated or it can have air in there, it doesn't matter. The first thing that happens when you close it off is all the movement of molecules from the liquid into the vapor phase is one direction, right? When you first start off, because there's nothing up here, not from the liquid, so it's all one direction. Eventually, you get enough up here so that they start returning to the liquid phase. So at some point and at a given temperature, you reach an equilibrium of evaporation versus condensation. And depending on the molecule, the type of compound, this will occur at different temperatures. And in general, the more polar the compound, the higher the temperature at which you reach equilibrium. So this is another way of expressing it. The rate of condensation starts at 0 because there's nothing in the vapor phase. But as you increase the amount of evaporation, you reach a point where the rates are equal. And then you have an equilibrium state of condensation versus evaporation. Now, at that given temperature, and it's characteristic of each compound, when you put that liquid in a closed vessel, you reach a pressure. In other words, you can measure the amount of pressure that's being exerted by that gas at that given temperature for that compound. And that vapor pressure is characteristic. So the vapor pressure of water will be a certain level, but if you have ether there, which is nonpolar, its vapor pressure will be much higher at that same temperature because you have more evaporation. There's less. The forces are not holding it in the liquid phase, right? You get more of it in the vapor phase before it starts returning, and you reach equilibrium at a higher vapor pressure for a given temperature. So the less polar the molecule, the higher the vapor pressure. So the vapor pressure of water at 100 degrees is 1 atmosphere, right? Because that's the boiling point at 1 atmosphere. Example, right? This barometer, if there's a vacuum up here and you're at sea level, 760 millimeters will be the height of that column. But if you put something up here, like water vapor, it will decrease the column by 24 millimeters. If you put ethanol up there, it'll decrease that column height by 65 millimeters. And if you put ether, it'll decrease the column by 545 millimeters. Right? So the more volatile, the more vapor pressure. And the lower the less polar will have a higher vapor pressure. Because there's nothing holding the molecule in the liquid phase, right? It just as soon be gas as liquid if there's nothing holding it behind. I already said that. So as your temperature goes up, your vapor pressure goes up. But for the where the intermolecular forces are much greater, the vapor pressure increases more slowly with temperature increase. Diethyl ether, by the time you reach 1 atmosphere, 34.6 degrees is its boiling point, right, at sea level. Whereas ethanol is 78.4 degrees, so that's the temperature that you need to get your mash to distill off the ethanol. Let's see, what is this? That is, oh, Clausius-Clapeyron equation. I think I was doing a derivation there. You don't have to know how to do that. I don't know if I could do it offhand. But it shows the relationship of the pressure to the heat of vaporization and the temperature. Right? So if your heat of vaporization is higher, since this is a negative, then your pressure is going to be lower. So it takes a lot of heat to vaporize, like water versus ether. Then your pressure is going to be lower. So this is the useful form of the equation is this. Right? So here's the temperature of this compound. Actually, it's the same compound. What's the pressure at this temperature here? What's the pressure at that temperature? If you make those two measurements, you can determine what the enthalpy of vaporization is. That's the whole point of this version of the Clausius-Clapeyron equation. Okay. So if you know the vapor pressure at that temperature, and you use this R value, right, the one with the energy component, and then the temperature in Kelvin, then you can calculate the heat of vaporization. How much heat does it take to vaporize that compound? Here's an example. So if you know the vapor pressure at 25 degrees is this many torr, and in this case you're given the heat of vaporization, then calculate the vapor pressure at 65 degrees. So what we're doing is we're using this equation where we know this one, and we want to calculate the vapor pressure at the new temperature, right? So it's like any equation. If you know everything but one unknown, you can solve for it.
The changes that occur as energy is added to a solid can be summarized by a heating curve. This section of the graph represents water in the solid state, or ice. Starting at a low temperature, we see that the temperature rises as energy is added. In this region, the added energy increases the motions of the solid molecules, but the molecular motion remains centered on a fixed position. This section of the graph represents the melting of ice to form liquid water. When the curve abruptly changes slope to zero, the solid is melting. Here, all the added energy is used to overcome the intermolecular forces holding the water molecules together in the solid structure, allowing the water molecules to move around more in a liquid state. There is no further change in temperature until all the solid is converted to liquid. This section of the graph represents water in the liquid state. Further addition of energy causes the water molecules to move around faster, increasing their kinetic energy. The water molecules are attracted to one another by hydrogen bonds, but the rigid structure characteristic of ice is no longer present. Water is more dense than ice because the structure is more mobile and the cavities present in ice are no longer maintained. This section of the graph represents the vaporization of water. In this area, the temperature remains constant again, in spite of the addition of energy. The added energy is used to overcome the intermolecular forces between the molecules in the liquid, changing the molecules into the gaseous state. The temperature remains constant until all the liquid evaporates. This section of the graph represents water in the gaseous state, or steam. Addition of energy raises the temperature because the kinetic energy of the molecules is being increased, and the molecules are moving around more rapidly. The molecules in the gaseous state are far apart and relatively independent of one another.
Okay, so this is characteristic, reasonably characteristic of phase changes, right? So as you increase the temperature, you're adding energy, but as long as it's in one phase and not another, temperature will increase. But once you reach the melting point, then it flattens out and all the energy is used to complete the conversion from solid to liquid. And then you get another slope and another flat and another slope. That is characteristic of heating curve. So, which would you predict? The amount of energy represented by the enthalpy of vaporization versus enthalpy of fusion. And the enthalpy of fusion is another word for the heat of melting, right? Fusion, melting, same thing. Vaporization, the amount of heat it takes to convert liquid to gas, or the amount of heat it takes to convert solid to liquid. Which one should be greater? Got a guess? Yep. Takes much more energy to convert liquid to vapor than it does from solid to liquid. Because the bonds that you're breaking are stronger, and here you're separating the molecules. They're virtually independent from one another, whereas solids and liquids are more closely related to one another in the intermolecular attractions. Okay, so that was a heating diagram. Now we've got one other diagram to show you, which is called a phase diagram. And what the phase diagram does is it combines information about the temperature of a substance and the pressure at these various phases. This is an idealized version. And between this one and this one in here is solid gas. So along this line right here, you have both solid and gas present at the same time. Whereas along this line, you have solid and liquid together. So if we hold the pressure constant and increase the temperature, then you go like this and you cross that line from solid to liquid. So at that point, the melting point at that pressure. If we keep going across there at that same pressure, then liquid to gas at this point is the boiling point of the substance. It goes from liquid to gas at that pressure. So what's happening here? See, this is melting, this is vaporization. What's happening here if you go from solid to gas? That's sublimation. You go from solid to gas, like dry ice. Right? So if the pressure is way down here, this low, then you can go from solid to gas as you increase the temperature. That's why when we freeze dry stuff, like freeze dry vegetables, fruits, coffee, to make those Folgers crystals, freeze dry it. You decrease the pressure. You go way, 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 way low pressure. Then as you add heat, you vaporize the solid water, the ice, into a gas. That's freeze drying. Oh, some other things. Okay, two other points. If this is solid and gas together along this line, this is solid liquid along this line, and liquid gas along that line, at that point, you have all three, solid, liquid, gas, together at the same time, at this pressure and that temperature. That's for carbon dioxide. Okay, that's the triple point. If you follow this line out to a very high pressure and relatively high temperature, not, well, 31 degrees, that's a little more than room temperature. Then beyond this point is the critical point. And at that point, you have a fluid, yes, it flows, but you can't tell the difference between liquid and gas. That's why there's no line out here, because it could be either one. It's neither. It's a phase that we don't fully understand, but it has been characterized as far as what you can do with it, right? So carbon dioxide in this region is used as a supercritical fluid to extract things from certain materials. We used to use it to extract compounds from plant materials. The reason being that it's very efficient, non-polar extractant from cells, plant cells, without destroying the compounds that you're extracting. And then you just remove that liquid into an environment where the pressure drops down to atmospheric, and the carbon dioxide goes, and you're left with your compounds. So it's a very gentle way of extracting compounds from plants, from my experience. Now, the phase diagram from water is kind of strange. Remember from CO2, the slope on the solid liquid line is positive, lower left, upper right. The slope on the solid liquid line for water is backwards. So at this temperature, if you increase the pressure, you're going to change solid to liquid. Now there was, at one time, the explanation for the way skates work on ice incorporated this idea, right? So you put your weight on a very narrow blade, you increase the pressure on that ice to the point where it turns to liquid and then you can slide. But that's been debunked. It doesn't explain it. In fact, the coefficient of friction between steel and ice is very, very low. So you don't need water as a lubricant, liquid water. Anyway, so as the intermolecular forces increase, what happens to each of the following? Right? So if you increase the intermolecular forces, you should get a higher boiling point. Right? Oops, I thought it was going to, I'm going to have to verbally give it to you. The viscosity increases as the intermolecular forces increase. Surface tension increases. The enthalpy of fusion, that is the amount of heat it takes to go from solid to liquid, increases with those increasing forces. The freezing point increases, and the heat of vaporization increases. The only one that decreases is vapor pressure. As you increase the strength of bonds between the molecules in a liquid, you decrease the amount of that liquid that can escape into the vapor. So all of these increase except for vapor pressure. It decreases. Okay? That's chapter 10. We'll take a break. Or do you want to talk about lab? Let me pause this thing so we don't need to record the lab. All right. So let's call up chapter 11, properties of solutions. Just covered liquids and solids. Now we're going to look at solutions in more detail. All right. All right, solutions. Remember our one earlier definition we had for solution was a homogeneous mixture. That's another way of saying a solution. But a homogeneous mixture could be of two different phases. It could be formed from two gases. That's fairly simple, right? The air we breathe is a solution. Or a liquid and a solid like salt water or sugar water. That's fairly intuitive. But other things can form solutions. Of course, antifreeze in your radiator, that's a liquid. Ethylene glycol in water forms that solution. But other solutions can be like brass. That alloy is a solution. You know, copper and nickel. Carbonated water is a gas in a liquid. That forms a solution. And some solutions can form from gases on solids. In this case, hydrogen on platinum. So solutions come in a whole host of different phases. Oh, here we go. Expressions of solutions. How do you express concentration in solution? Well, and we didn't cover molarity, did we yet? We are now. Molarity is the number of moles of solute. Remember, in solution, the solute is usually the minor component, and the solvent is the major component. So when you throw salt in water to make a saltwater gargle, there's just a little bit of salt in a lot of water. So in that case, the salt is the solute and the water is the solvent. If you start out with sugar dissolved in water, the sugar is the minor component dissolved in water. But sugar, sucrose, in water is unique. Well, not unique. I say it has very high solubility. Let me put it that way. It has such high solubility, before you reach a point where you can't put any more sugar in it, you've actually got more sugar than you do water. But since we started out with water as the major component and sugar as the minor, we still call sugar the solute and water is the solvent. Now, how do we express concentration? For molarity, moles of solute per liter of solution. Moles per liter. And this is of solution, liters of solution, and moles of solute. We'll give you an expression of concentration. Another way to express concentration is weight, percent. Right? So if you have, if you know the mass of your solute and the mass of the solution, all you have to do is divide the solute by the solution mass times 100, and you have percent, weight. Now, that's the problem with percentage is you have to specify whether it's weight or volume. So weight, mass percent. Well, it's understood to be mass percent is mass, which is mass of solute per mass of solution. So this is the mass of the solution. This is the mass of the solute. Okay.
So it's just basically N equals N.
Yeah. Right. So you have the mass of the solute, and these have to be the same units of measure. Doesn't matter what they are, grams, kilograms, as long as they're both the same mass units. And then mass of solution times 100, which makes it percent. If we say percent, something percent, like alcohol by volume, ABV, that's let's see. I think that's volume. So volume of ethanol in volume of solution, percent. But you can also have percent mass volume. So the mass of the solute, but then the volume of the final solution. Right? So that's the trouble with percent. You have to specify whether it's mass or volume of each component. Okay, let's see. I'm running out of room. So let me go over here. This mole fraction is useful, and it's exactly what it says. It's a fraction. So if you have A and B mixed together, if you have solute in your solvent, you know the total moles of solution, then the solute, moles of solute on top and the total moles on bottom gives you a fraction. That's not going to get picked up. Put it on the other side. There we go. Mole fraction of the solute. So the advantage to that is you're able to deal with actual numbers of atoms and molecules, whatever the case may be. Mole fraction. It's particularly useful for expressions of gases. And then molality, we covered that a little earlier. Little m equals molality.
Everything's a little m.
Yeah, I'm sorry. Little m for mass, little m for molality. That's why I wrote this up here, so it wouldn't make that mistake. So that one is, again, moles of solute per kilogram of solvent. So this is the one where the denominator is not solution, but only the solvent. It's relative to kilograms of solvent. Those are the most common concentration expressions for solutions. Molarity. The advantage to molarity is that if you know what the molarity is and you possess a certain amount of solution, you can calculate how many moles of solute you have. Right? It's like any equation. You've got three unknowns here: molarity, moles of solute, liters of solution. If you know any two of those, you can solve for the third. So in this case, if we have a mole of sugar in 125 milliliters of solution, what's the concentration in molarity? Well, you got to remember, what's the definition? Moles per liter of volume. So we know the moles is 1 for sugar, and the total volume is 125 milliliters. So how many liters is that? One, two, 0.125 liter. Okay. Then you can calculate the molarity. It should be 8 molar solution. Okay. This one just flips it around. If you know that you have 10 molar sugar solution, so now we know what this value is. And the volume, what volume do we need to give you 2 moles? So that's equal to 2 moles, and this is unknown. All right, so we just solve for this one. We go over here, that one over there. 2/10 is 1/5, 0.2, right? 0.2 liters or 200 milliliters. Okay.
So you just divide what's in by the 2.
Yeah. Just move this one over here, right? When you cross the equals, it moves from the denominator to the numerator and numerator to the denominator. So V equals 2 divided by 10. Right, just algebra. Let's see. In this case, you're given mass and a final volume. So what do we need to do to use this equation? We've got to convert that mass to moles, right? So 100 grams of sodium hydroxide converted to moles, what do we need? Got to get rid of grams, leave us with moles. So when you have grams on one side, moles on the other, you're talking about molar mass. So sodium is 23, oxygen 16, and hydrogen is 1.01. It's 1, 0, 7, 40. 40.1, 0.01, excuse me. So that'll give us the number of moles. So 40 into 100 is about what? 2.5? About 2.5 moles. So if we divide 2.5, well, that's mole.
It is 2.5.
Okay. 2.5 divided by 0.25 liters, right? Because it's 250 milliliters. 0.25 liters should be ten molar. 10 molar. Okay, so that's for sodium hydroxide. Potassium chloride would be 39.1, and chlorine is 35.45.
You do
74.
the 100 again.
Huh?
You do the 100
Yes.
again.
They're both 100 grams. So we substitute this one in here, divide that into 100. Where that has to be?
That's 74.
74.55. So that's 1.34 moles and 0.25. So I get 5.4 molar. So for the same mass of each of these, sodium hydroxide, potassium chloride, you get a different concentration because it calculates out to a different number of moles of each one. Okay, so I'll round it. Mass percent. Yeah, we're doing on time. Got till 5:50. Okay, we're good. Mass percent, that definition. What's the percent by mass of glucose when you put 5.5 grams in 78.2 grams of water? Okay, so what's the mass? 5.5 grams of sucrose. What's the total mass? That's just the water, right? So the total mass of the solution, you have to add them together, times 100. .6%. And to be safe, let's put mass percent. That was so easy it only deserved one slide. Mole fraction. Okay. So in order to do mole fraction, we have to know how many moles of solute and then how many total moles in the solution. So in this problem, we have a solution of phosphoric acid dissolving 8 grams of phosphoric acid in 100 milliliters of water. What's the mole fraction? Right. This is complicated, looks like, but if we go back to our definition, mole fraction of phosphoric acid, we need to know the moles of phosphoric acid. Then we need to know the moles of phosphoric acid plus the moles of water.
So 8 over 8 plus 100.
No, mole fraction. That's mass. We got to convert it to moles, right? So the moles of phosphoric acid would be 8 grams. And then we got to convert that to moles. We got grams, moles. So we need phosphoric acid, which would be, the hydrogens are 3.03, right, because there's 3 of them. Phosphorus is 30.97. And 4 oxygens, 16 times 4. Let's figure that one out. I get 98.
So in order to figure out that, like, the H3PO4, that's all you have to do is add their,
Add their atomic weights together, and that gives you the molar mass of the H3PO4 molecule. We'll divide that into 8. 8.16 times 10 to the minus 2. 8.816 times 10 to the minus 2 moles of phosphoric acid. Now we need the moles of water. So we've got 100 milliliters of water. 100 milliliters of water. We need to convert that to moles of water. So we need to know the mass of the water before we can convert it to moles, right? Using the molar mass of water. So the density they're saying is 1 gram per mil. We're assuming that. So 1 gram per mil gives us 100 grams of water. Then we want to convert grams to moles of water. So water is H2O, so it's 16 plus 2.02, which is 18.02. So 18.02 into 100 is 5.55 moles of water. Okay, now we can finish this one. So we got 8.16 times 10 to the minus 2, for that one. And this one is 8.16 times 10 to the minus 2 plus water, because this is the total. Actually, that's so small we can probably ignore it, right? So 5.55, and then 8.16, 6 exponents plus, it has some value. Let me try that again. I don't like the way that one turned out. Okay, that's 5.63 divided into 8.16 times 10. This is all moles. So there we go. So I get 1.45 times 10 to the minus 2 What would that be in standard notation? Move 2 places, right? 1, 2. So there's the mole fraction. For that problem. Okay? Molality. So what would the molality be for this one? Well, molality, let's see, I don't want to. There's the moles of our H3PO4, so we'll keep that. And we'll change this up here, the molality of H3PO4. So we got moles on top, that stays the same. That's 2 moles. Now we need kilograms of water. How many kilograms is 100 grams? 0.1 kilograms, right? 3 places? 1, 2, 3. So we divide that into it, and we get 8.16 times 10 to the minus 1, or 0.816 molality, I think. Yeah. Keep up with what am I doing here? Okay. All right. So those are the ways to express solution concentration. Now we're going to switch gears a little bit. And we're going to talk about theory, actually. A way to visualize how solutions form. They can be looked at as a 3-step process. First of all, the solute, of course, has intermolecular interactions. And before that each solute molecule or atom can go into solution, you have to break the bonds between those solute molecules. All right, so that's step 1, called expanding the solute. So you have to put energy in. So step 1 is energy input. Step 2, you need to make a space in the solvent for those solute molecules. Right? That's called expanding the solvent. In that case, you need energy input because you're breaking bonds to separate, making holes in your solvent. So their energy goes in. Now, once you've got those holes and you put these two together, the solvent interacts with the solute. And in that case, you get energy output. Because as they come closer together and start to interact, they give off energy. So the first 2 steps, you put energy in. Third step, you get energy back. Now the total, actually to be accurate, this should be delta H. Sorry. Now the overall enthalpy of solution is the summation of these 3. So if you put in a whole lot of energy here and here, and you only get a little bit back, this is going to be positive. Right? It takes a lot more energy going in than you get back. Right? So what does that mean in terms of temperature? Well, if you put more energy in here, here, and you only get a little bit back, then the solution should get colder, right? Put energy in high here, only get a little bit back. It should get warmer. But if you put in a little bit here and a little bit here, and you get a whole lot back, then this should be, you get energy back, it should get warmer. Now, in terms of sign, what does that mean? Remember the sign convention? Exothermic is negative, endothermic is positive. So in the first case, you get a positive delta H. In the second case, you get a negative delta H. Because negative is exothermic. Let's see. That just says what I already said. Right. So if delta H is positive, energy is absorbed, and the solution gets colder. If delta H is negative, the energy is given up, and the solution gets warmer. All right, let's see. Okay, so let's say oil and water. So this is the solute. This is the solvent expansion. This is solute expansion. And this is the solute solvent interaction. Step 3. Okay. So if the solute is oil and the solvent is water, we put energy in to separate the oil molecules, energy in to separate the water molecules, then do you get any energy back? Is there any interaction between the oil and the water? No, because oil is nonpolar, water is polar. They don't like to interact. The forces don't complement one another. So even if you put a lot of energy in, you're not going to get any back, and you don't form a solution. So that was an example. Let's look at it in general terms. Suppose you have a polar solute and a polar solvent. Okay, how much energy? Let's remove these. Let's say this is polar, this is polar. How much energy does it require to expand this one and that one? If they're polar, then they're very strong interactions. So there's a lot of energy required for both of them. But when they come together, you get this large interaction, right? You get a lot of energy back. Let's say input, input, and you get a lot of energy back. So they basically balance one another off together. They balance, and your heat of solution is relatively small, but the solution forms easily, simply because they're both polar. Let's go down here and look at nonpolar, nonpolar. So if it's nonpolar for both of them, how much energy is required to get them apart? Very little. The forces holding those together, the expansion is very inexpensive energy-wise. But when they interact, how do they interact? Well, they interact about the same as they did before, very weakly. But they still form a solution, right? Because they do interact, nonpolar, nonpolar. So those are the two extremes, polar, polar, nonpolar, nonpolar. What about nonpolar polar. Because if we can explain this one, then you just flip it, same explanation. So if you have a nonpolar solute, it takes very little energy to expand it. And a polar solvent takes a lot of energy to expand it. But do you get any energy back? Polar and nonpolar don't like each other, right? The forces attracting them are very low. So you get no solution. If we just flip this up here, same result. You get no solution with nonpolar and, let's see, nonpolar polar or polar nonpolar. No solution forms. So all of that is designed to confirm the rule of thumb. Like dissolves like. I know you heard that one before. No? You have now. Like dissolves like. So polar solvents dissolve polar solutes very easily, readily. Nonpolar solvents dissolve nonpolar solutes very readily. Okay? And the converse of that is oil and water don't mix. Right? When you make up salad dressing, you put vinegar and oil together with some spices. And if you just let them sit there, you have 2 layers, right? That doesn't do your salad much good. You have to shake the hell out of it to emulsify it, and then pour it on your salad quick before it disperses. Because it will separate. Because oil and water are not like, and they separate. All right, let's see. I went the wrong direction. Here we go. All right, so we just discussed factors affecting solubility. Right. Polarity was the first one. Right. So 2 polars dissolve, 2 nonpolars dissolve. Nonpolar polar don't dissolve. But those are not the only effects. If you're dealing with solutions that involve gases dissolving in liquids, then pressure effects are significant. You know, that's why your 2-liter bottle of pop has a seal cap on it. And when you open it, it goes, psh, right? Because the pressure inside is sufficiently high to help drive the gas into solution. And then there are temperature effects. These effects are valid for any type of solution, but we're going to focus on aqueous solutions. So pressure effects are governed by Henry's law. Temperature effects are a little more complicated, and they vary depending on the solvent and the solute. In general, when you try to dissolve a solid in a liquid, increasing the temperature increases its solubility. There are some exceptions. Terminology. Hydrophobic means water-fearing, which generally means nonpolar. Because water is polar, then a nonpolar substance doesn't want to go into water. It's afraid of water. Hydrophobic. Hydrophilic means water-loving. Those are polar substances because water is polar. Okay, here's Henry's law. C is the concentration of the dissolved gas. Right? So the concentration varies with the partial pressure of the gas above the solution. Right? So if we have something like this, you have a solution here with gas molecules dissolved in it. and you'll have some up here too. You increase the temperature, you are increasing the energy of these gas molecules, and that makes them leave the surface more readily than they would otherwise. So what happens is, actually, excuse me, Henry's law is for a particular temperature. So you hold temperature constant, then you vary the pressure. If you increase the pressure here, then you drive these gas molecules into solution. So the higher the pressure here, the higher the concentration. And K is an empirically determined constant. But the concentration of the gas is directly proportional. Right? This is a direct proportion. Okay, so here's the liquid. It's kind of hard to see. Here's the liquid surface. We increase the pressure by decreasing the volume. You know, just push it down. Then you get more of those gas molecules in the solution. So the temperature effects. This is what I said before. In most cases, increase the temperature, you get more of your solute in the solution. But it's very unpredictable. It's difficult. Usually what you have to do is just develop charts, publish charts, and read them off. Formula is very complicated and not often reliable. That's for a solid dissolved in the liquid. For a gas dissolved in a liquid, it's just the opposite. You increase the temperature, then more of these gas molecules come out of solution because their kinetic energy is higher, and at the surface of the liquid, they have more energy, so they migrate to the gas phase. Okay, so that's why your 2-liter Coke bottle at room temperature gives you a big when you open it. But if you stick it in the refrigerator for a couple of hours, when you open it, it gives you a little, because lower temperature, more gas dissolved in your pop. So if you cool your pop down before you open it the first time, then you can open and close it many more times before it runs out of its fizz. That's why I never, well, not never, I avoid, whenever possible, opening my pop bottles until they've been cooled in the refrigerator. Practical application of theory. Okay, so this illustrates the solubility of solids in water. Yes, water. Okay, solubility, so many grams of solute in 100 grams of water. In most cases, as the temperature goes up, the solubility goes up. It's different for each one. Right? Sugar goes way up. Potassium nitrate goes up. Sodium nitrate up. Bromides go up. Potassium chloride goes up. These sulfates, sodium sulfate and cerium sulfate, goes down as you increase the temperature. Solubility of gases in water, right? So as you increase the temperature, solubility goes down. Except helium is almost flat. So as you increase the temperature, its solubility, and it starts out very low solubility. Okay? We used to use that fact in the laboratory. We had this instrument called a high pressure liquid chromatograph. So you'd have this column with packing in it and use it to separate compounds. Right? You drive the compounds through the column, and their differential absorptivity to that packing versus the mobile phase will allow you to separate them. But the problem is you don't want a lot of dissolved gas in your mobile phase as it moves through there because it's under very high pressure, hundreds of atmospheres on one end. When it comes out the other end, the pressure drops off to nothing, to 1 atmosphere. If you have a lot of gas in it, that gas will come out of solution like that and destroy your detector. Right? So what we used to do is bubble helium through the mobile phase, and it would drive out, it would displace all these other gases, and its solubility was so low that then we could drive it through our HPLC without fear of affecting the detector. So what happens if you have an aqueous solution in one jar and pure water in the other? And the solute in here is non-volatile. In other words, it will not come out of solution. It's like a salt solution, say. What happens over time? Well, if this vessel is closed, which way is the water going to move? The water leaving this solution into the vapor is much lower pressure than this side. So the net movement is water moving over like that. If you leave it in there long enough, this one will dry out, and all of those, and most of those, water molecules will end up over here in that solution.
At the boiling point of a pure liquid, a dynamic equilibrium is established between molecules in the liquid phase and molecules in the vapor phase. Some molecules at the surface of the liquid have enough energy to leave the surface and enter the vapor phase. Some molecules in the vapor phase collide with the surface. At equilibrium, the number of molecules leaving the surface is balanced by the number of vapor molecules that return to the liquid phase.
Okay? So for a particular temperature, in a closed vessel, you eventually reach an equilibrium point between the vapor phase and the liquid phase. What happens?
The new liquid-solute interactions change the nature of the liquid phase. As a result, fewer molecules of liquid leave the surface to enter the vapor phase. The reduction in
Those yellow dots are non-volatile solute, like salt water. So what they do is, at the surface of the liquid, they're there, but they're not volatile. So they reduce the number of positions that are available for water to leave the surface. So they decrease the vapor pressure of water in that case.
the number of vapor molecules leads to a lower vapor pressure. A new dynamic equilibrium is established for the solution at a vapor pressure lower than that of the pure liquid.
Okay. Problem. There we go. So this can be expressed mathematically with Rayleigh law. As long as the solvent, the solute is non-volatile, you have this little zero means the vapor pressure of the solvent at that particular temperature. Pure solvent. Okay. This is the vapor pressure of the solution. Once you know the mole fraction of the solvent. So remember we calculated the mole fraction of, what was it, phosphoric acid. Okay, that's the mole fraction of the phosphoric acid. What's the mole fraction of the solvent? It's 1 minus that value, right? So what's left over? There's only 2 of them, and they got to both add up. Since they're fractions, they have to both add up to 1. Right? So you just subtract that from 1, and you get the mole fraction of the solvent. So we have the vapor pressure of the solvent when it's pure times its mole fraction, and that gives you the vapor pressure of the solution. Very simple. In fact, it's a linear relationship. So if the mole fraction of the solvent, actually, if the mole fraction of the solvent is 0, there's no solvent there, so you don't get any pressure, right? So as you increase the amount of solvent, vapor pressure increases. If it's ideal, it's a linear progression until it's pure. And then this is the vapor pressure of the pure. Okay? What happens if you have two volatiles together? Well, we have to modify Rayleigh's law to take into account the volatility of each. So if you have the vapor pressure of the pure A and the vapor pressure of the pure B, then all you need is the mole fraction of each. And you can calculate the total by knowing the mole fraction. Now, if there's 0 interaction, molecular interaction between A and B, then you get an ideal expression. And here's what it looks like. Here's the partial pressure of A as its fraction increases. And here's the pressure of B going the other direction as its fraction increases. So as A increases, B decreases. And the vapor pressure of the solution is connecting the pure B to the pure A point here. That's an ideal solution in which there's no interaction between B and A. Okay? But more often than not, there is some type of interaction. All right? If there's an attractive force between A and B, then you get this strong solvent-solute interaction. They attract one another. Then you get a depression in the vapor pressure curve, like that. If there's a weak interaction, or even a repulsion for that matter, you get this convex versus concave interaction. So this signifies a strong interaction between the two. This signifies a weak interaction between the two. Examples. So if the interactions are basically the same, AA attracts, interacts, BB interacts, and if AB is the same interaction, attraction, whatever, between these two, then you get an ideal solution. And benzene and toluene is an example. They're both organics. They both have similar interactions amongst their individuals as they do when they put them in solution. So you get an ideal vapor pressure curve for these two. However, if the interaction between A and B is a strong interaction, such as between acetone and water, stronger interaction between those two as with each other, then you get that negative curve, or the concave curve. But if you try to put ethanol and hexane together, they will go into solution, but they don't interact very strongly. Right? In that case, you get a positive deviation. Let's see. Which ones of these would be ideal? Which ones would give you the same type of interaction between the two as within each other? Okay. Hexane has very weak interaction with itself. Chloroform is slightly polar, so it's going to have a stronger interaction. Right? So the interaction between the two would not be the same. How about ethanol and water? Well, water's polar, and ethanol is slightly polar, but it's not as polar as water. So those two wouldn't be ideal. Hexane and octane are both hydrocarbons, and they have similar interactions between the two, both internal and when you mix them together. So this one would be ideal. Now, the trick is trying to figure out which one is a positive deviation, which one's a negative deviation. So in order to be a negative deviation, we need a stronger interaction between the two in solution than they have with each other. And I think because this one is polar, that one's polar, this one will be the negative one. And since this is non-polar and that's slightly polar, this one would be the positive deviation. Let's see. Oh, I thought it was going to give me an answer. Well, that's what I think. This would be ideal. This would be a negative deviation. This would be a positive deviation. Okay, what's a colligative property? Colligative is a fancy word for, it doesn't matter what the solute is. You can put any solute in. If you know the number of moles going in, it's going to behave exactly the same way, whether it's this solute or that solute. That's a colligative property. It only matters how much. These are the three most common colligative properties that are described. We talked about freezing point depression earlier. Boiling point elevation is similar to freezing point depression in that, let's see, am I going to have to draw this or is there a slide for it? Well, we go with freezing point depression it talks about. But boiling point elevation is still just a delta T. Right? So that's an absolute value. How much does it change? Then you have a K value for your solvent, and then the molality of the solute. Right? So this is empirically determined. You have to be given that value. Or if you're given this one and this one, you can determine it. But for our experiment, you're going to be given that part. You're going to measure this part, calculate that part. Osmotic pressure. Let's see. Anatomy and physiology. Y'all had that? Okay. So you understand what osmotic pressure is. Okay, good.
At the
Let's see.
boiling point of a pure liquid, a dynamic equilibrium is established between molecules in the liquid phase and molecules in the vapor phase. Some molecules at the surface of the liquid have enough energy to leave the surface and enter the vapor phase. Some molecules in the vapor phase collide with the surface. At equilibrium, the number of molecules leaving the surface is
That's wrong.
addition of a non-volatile, the new liquid solid at the freezing point of
Here we go.
a pure liquid.
That's the one I want
A
you to see.
dynamic equilibrium is established between molecules in the liquid phase and molecules in the solid phase. Some molecules at the surface of the solid have enough energy to leave the surface and enter the liquid phase. Some molecules in the liquid phase collide with the surface. At equilibrium, the number of molecules leaving the surface is balanced by the number of liquid molecules that return to the solid phase.
Okay, so that's at the freezing point of the pure substance. What happens when you add a solvent to it?
Addition of a non-volatile solute, shown here in yellow, will change the dynamic equilibrium established at the freezing point. The solute does not enter the solid phase. The presence of the solute changes the nature of the molecular interactions in the liquid phase. In addition to liquid-liquid interactions, there are now liquid-solute interactions.
So, since you have fewer of the liquid molecules entering the solid phase because of this interference of these solutes, it takes a lower temperature to overcome those interactions and to get it into the solid phase. So that's why we say freezing point depression. It takes a lower temperature to freeze it there. That's why your ice cream freezer works. You add salt to your ice, it lowers the freezing point of the ice, and eventually you reach a point where you're actually below the freezing point of the custard.
The new liquid-solute interactions change the nature of the liquid phase. The solution will stop freezing as the temperature drops. The solution freezes at a new, lower temperature. A new dynamic equilibrium is established at the new freezing point.
Okay. Boiling point, freezing point of water. So if we're going to change the vapor pressure and freezing point, and boiling point for that matter, what we see is a shift. This change in freezing point at a given pressure shifts that whole curve this way because we've got to decrease the temperature. But the boiling point has to shift up. Boiling point elevation shifts what direction? Boiling point of water, boiling point of solution. Okay, so we shift this way. The blue is the new, and the red is the old, the pure water. So we shift this one this way, we shift boiling point that way, and it actually changes the triple point as well. It moves it down here to a lower temperature. Let's see, solution was prepared by dissolving 25 grams of glucose in 200 grams of water. The molar mass of glucose is 180. What's the boiling point of the resulting solution? Glucose is a molecular solid that's present as individual molecules in solution. Well, let's see. I was looking for, I think we're missing some information. Because we need, yeah, we don't have the value. Yeah, we can't use this formula because we don't have that value right there. But let's do it qualitatively. If you add 25 grams of glucose in this much water, is the boiling point going to go up or down? Think of the definition. What does it say? Boiling point, elevation, right? Boiling point's going to go up. And if we had all the information we needed, we would be able to calculate. But it went up, not by much, but some. 0.35 degrees. Now, what happens to the calculation if we put a solute in there that breaks apart in solution, right? So if you put a mole of sodium chloride in water, how many moles of individual particles do you have? 2, right? Sodium chloride breaks apart into 2 moles sodium ions and chlorine ions, as opposed to 1 mole of sodium chloride. So that's this factor, the Van Hoff factor, I. Moles of particles in solution versus moles of solute dissolved. In this case, it would be for sodium chloride, I is 2. So you would take this and multiply it by the Van Hoff factor. What if we used calcium chloride? What would the Van Hoff factor be? And this is ideal. You know, there are some deviations. 1, 2, 3. Okay. How about, let's see. Calcium phosphate. 3, 4, 5. Okay. So if you take into account the how these things break apart, then you can determine what your Van Hoff factor is. The deviation from ideal is that even in solution, sometimes these ions come back in pair, right? So the true I is going, in this case, be less than 2, less than 3, less than 5. Because this ion pairing, because when you ion pair, now you only have 1 where you had 2 before. So that decreases the size of the Van 't Hoff. Sometimes not very much, sometimes a whole lot. Okay, that's the modification to the equation. You just stick an I in there, which is equal to the number of ions that break apart from your solid as you put it into solution. Let's see. We're 30 and we got till when? 5. How much more do we got to go? I don't want to eat up all our time. We'll come back to this if we have time. Oh, I actually worked this one out. Okay, so what was the question? Calculate the mass percent. Okay, we could do that. Composition of the original mixture and the mole fraction of sucrose in the original mixture. Okay, mass percent, we just need total mass. So we add our solvent together. And then we say mass percent, where is it? Molality. Here it is. No, that wasn't the question. That was mass percent, and then the mole fraction. So I must be doing mole fraction here. All right. Looks like a way to do it the old-fashioned way. So the mass percent, we need to know the total mass. 20 grams of sucrose and sodium chloride, and dissolve it in 1 liter of water. So the mass percent of sucrose would then be 20 grams mass percent. And then the total mass. Oh, the mass percent, this is going to be, this is total sucrose and sodium chloride. Right. Dissolved in 1 liter of water. So 1 liter of water weighs what? Roughly 1 kilogram. So 1 kilogram, and that's 0.02 kilograms. Right. So that's 1020 grams times 100. So that'll be your mass percent of the solutes. The mole fraction of sucrose. Oh, this is a lot of work. That's why I put it there. Because this is the mass, sodium chloride is 20 minus the mass of sucrose. There's the moles of sucrose is that mass of sucrose divided by its molar mass. Right. All right. That's why I put it in there, then I wouldn't have to think about it. So we got some algebra to do here. So the moles of sodium chloride then is 20 minus the moles of sucrose. Right, divided, well, by the mass of sucrose, divided by its molar mass. So then the molality of the solution is 1 kilogram of Yeah, 1 kilogram of solvent, right? Because it's 1 liter. Right? So there's your kilogram. And this is the moles of each one. So this is the molality of the solution, where X is sucrose and 20 minus X is sodium chloride. Well, what happened? I think I'm missing a slide. I got them out of order. That's the problem. All right. I'm going to let you look at that. See if you have any problems like that in your homework. Okay, what kind of question is this? If this is concentration molality in a plant cell, 0.25, you put it in an aqueous solution with a freezing point of minus 2.46. Will the cell explode, shrivel, or do nothing? All right. This sounds like a osmotic pressure problem. Right? So that's the molality inside the cell. What we need to know is the molality outside the cell, don't we? So if we take this freezing point of the solution, the aqueous solution, then we can find the molality, because all we need is delta T equals K molality. Right? We know this one because the change is 0.246. And then for water, we have to be given that value. Water, 1.86 is that K value, and then molality. So we solve for molality, and it turns out the molality of the solution outside the cell is 0.132. What was it inside the cell? 0.25. 0.25 molal inside the cell. And this outside the cell. Which way is the water going to move? Into the cell, out of the cell. Into the cell. Water is going to move into the cell. This is the solution. So the cell is going to explode. Right? We're going to move more water into the cell because it's a higher concentration than outside the cell. What kind of solution is this called? Hypotonic. Right? Okay. Heard the story of a high school teacher that was trying to show the class blood cells, right? So he pricked his finger, smeared it on the slide, and it was messy, so he wanted to, put it in some sort of suspension. So he put a couple of droppers of distilled water on it, put the cover slip on it, stuck it in the microscope, there's nothing there. In that amount of time, those cells absorbed water because it was distilled, absorbed water, and they all ruptured. So you had nothing to look at. So the moral of that story is use an isotonic solution. Okay. Osmotic pressure. So if you have a solution inside this device, and there's a semi-permeable membrane there, so the only thing that can go through it is water or smaller molecules than that. I think a better term for that is selectively permeable. right? Because you can get various compositions of those membranes that will let certain things through and not others. So in this case, it's only going to let water through. So as water passes through there, pure solvent, or water in this case, moves into this solution and starts to build pressure in it. So at some point, you build pressure in there until the pressure of the water moving in is balanced by the height of the column of pressure above it, right? So you get an equilibrium. And at that equilibrium point, you have a balance in osmotic pressure, right? And that's one way of measuring it. Oops. There we go.
When two solutions with the same solvent are separated by a semi-permeable membrane, solvent molecules migrate through the membrane from the solution of low concentration to the solution of high concentration. A concentrated glucose solution is added to an inverted funnel with a semi-permeable membrane, and the funnel is placed in a beaker of pure water. Water flows from the beaker into the funnel. The upward flow of solvent stops when the pressure of the solution above the membrane equals the osmotic pressure, pi.
Okay, so pi is the symbol we use for osmotic pressure. And in this example, we have pure solvent here, solution there, and as pure solvent moves, we reach an equilibrium point, and the difference between these two then is also the osmotic pressure. But that can be expressed mathematically as pi equals I MRT. So what are those? Well, the osmotic pressure and the expression of osmotic pressure depends upon the values over here. So R, I assume, is the gas constant. T is the Kelvin temperature. M is the molarity, and I is your Van Hoff factor. That should be for consistency. Yeah. If your solute doesn't break apart, then you can ignore the I. Right? The Van Hoff factor is not needed. So if we have 33.4 milligrams of a compound dissolved in 10 milliliters of water at 25 degrees C, the solution has an osmotic pressure of 558 torr. Calculate the molar mass. So you work these backwards. If you want to know the molar mass or the molecular weight, you need to know mass in grams and moles, right? So we know the mass, 33.4 milligrams. So 33.4 times 10 to the minus 3 grams. Now we just need to figure out how many moles. Well, we can use osmotic pressure is equal to MRT. We don't need I because we're specifying that we have no dissociation of the molecule. So we don't need the Van Hoff factor. Temperature then is, here we go. If we use the universal gas constant here with liters, atmospheres, moles, and K, and we make the atmospheric pressure in atmospheres, the pi in atmospheres, the universal gas constant is 0.08206. Right? Temperature in Kelvin would be 25 plus 273. Right? Then we just need, what's the molarity? Well, that's our unknown because we know what the pressure is. It's 588 torr divided by 60. That's its conversion to atmospheres, right? Convert that to atmospheres. Then we have this molarity, solve for molarity, and this is the molarity, but we need to know how many moles, right? So we have the molarity, and the molarity is, the number of moles is molarity times volume. So we were given the volume, right? There's the volume, 10 milliliters, or 0.01 liters. There goes liters times molarity. There's the number of moles. Now we've got the mass, we've got the moles, calculate the molar mass. Remember when we were doing empirical formulas, molecular formulas based on first percent composition, then you had to know what's the true molar mass in order to go to the next step. Remember that? This is one of the ways to find it. By this method, gives you that molar mass independent of the percent composition. Freezing point depression, boiling point elevation, those are two other ways of doing it. They're not the only ways, but good enough for students, right? Okay, so those are colligative properties and how to use them. Now we just got to colloids. What's a colloid? The key to understanding a colloid is particle size. A colloid is not a solution because the particles are suspended. They don't go into holes that were created by that 1, 2, 3 solution model. Okay. They just bounce around in solution and they interact with the solvent in such a way that they stay perpetually suspended. Okay? Now, how do we know the difference between a solution and a solvent and a colloid? Or a suspension for that matter? Well, the best way to do it is with the Tyndall effect. So you have a glass container, you have your mixture here. You're trying to decide if it's a solution or a suspension. And a colloid is a type of suspension. You take a bright light, right? Shine it through your solution. If it comes out the other side, you don't see it in there, right? You can't see the beam in here. That's a solution. If you see some of the beam in there, that's a suspension or colloid. If it's a true suspension, then eventually the solid particles will settle out. But if it's a colloid, they won't settle out, but you'll still get that Tyndall effect. Okay. So we're going to do some work in the lab later on, and in the titration that we do, we need to know when does silver chloride form during our titration. Silver chloride is very difficult to see. First of all, the particle sizes are very small. So by the time you see the cloudy effect from that precipitate that forms, because silver chloride is insoluble in water, you're past the endpoint. Right? So what we do is we take a bright light and dim the lights and shine it through the solution as we try to titrate it with our sodium chloride, I think. So I always keep a bright light with me. And you just, one person hold it like that, shines it through the solution as you titrate, and then you can see better when it forms because you'll see this Tyndall effect. I think I've incorporated that into the method, so when we get there, you'll see it already. Particle size. So very large molecules will not remain in solution, but smaller molecules in the range of maybe 1 to 1,000 nanometers will remain in solution, suspended, and sort of mimic a solution, but they're not really a solution. And the way they mimic a solution is they stay suspended indefinitely. Okay, these are other types of colloids. This type of colloid was a solid in a liquid. But there are other types of colloids. If we have a liquid dispersed in a gas, it could be an aerosol, or a solid dispersed in a gas, we call that an aerosol also, those two. If we have a gas dispersed in a liquid, we call that a foam, right? If we have a liquid in a liquid, we call that an emulsion. So if you are able to reduce the particle size in your salad dressing far enough, you could end up with an emulsion. Mayonnaise is a better example. Milk, not pasteurized, homogenized milk. You know how they homogenize milk? They take the milk and they, under high pressure, they push it through a disc that has very, very, very small holes. And that takes all the fat globules. And when they come out the other side, they're microscopic, on the order of 1 to 1,000 nanometers. That way they stay suspended, right? That's homogenization for milk. Mayonnaise is an emulsion based upon the effect of egg. Egg whites are effective emulsifying agents, so they maintain everything else in this colloid. Gelatin is a solid in a liquid. Gas in a solid is a solid foam. Right? This was a liquid foam. This is a solid foam. A liquid in a solid is a solid emulsion. And a solid in a solid is a solid, ruby glass. So probably the first laser that was ever developed, the ruby laser, was a solid salt. So what do we mean by coagulation? Well, if you have a colloid, you know, something suspended in that medium, all you have to do is cause it to lose its physical integrity. In other words, change its shape, then it interacts with the dispersing media differently. And in that case, it might drop out of solution. So that's what we do when we, let's see, examples. Oh, making cheese. When you coagulate the curds from the whey, you're destroying that colloid in the milk by causing the protein in the milk to change its shape, and then it clumps together, drops out of solution. Some of the best ways to do it, heating or adding an electrolyte. You change the charge on the molecule, and then they stick together, drop out. Actually, with making cheese, you add an enzyme called rennet that they get from sheep stomach. And that causes the protein to coagulate from that enzymatic reaction. Okay, I've said enough. Been a long day. Okay, so has anybody tried yet to get into Cengage? Okay. Based on my last class and their experience, when you go to that website, you should have in hand your code that Unlimited gives you when you buy it. You should have a code there. Put that code in, and that allows you to form your, to create an account. And then when you go into
only need to get like the 6-month subscription.
Yes, right, because this is the end of your, right, chemistry. Unless you're gonna come back next semester and take another course that uses Cengage.
The MLT thing you Cengage?
Huh?
The MLT thing you Cengage? MLT.
I don't think so. No. So probably 6 months is good enough. Let's see. Let me call up Blackboard.
That business too big to.
Oh my God. I've been missing stuff.
There it is. Blackboard. And we're gonna sign in. Close the fingers. There we go. So we'll go to our course. 1, 2. And if I start here, here's the homework connection. Yeah, there it is right there. Then block. Oh, pop-ups aren't enabled. Okay, so I got that enabled pop-ups. Ooh, I better make it that. Somebody mentioned that earlier. They were blocked.
So this homework for these 2 chapters are due by Wednesday,
Exam day.
exam day.
Hold on a second. Let me make this up a note. Block equals pop-ups. So you have to enable pop-ups. Let's see. So I'll go over here, I think, to options. Privacy and security. Permissions. Here we go. This one says block pop-up windows, so we can unclick that one. And that should allow us. Let's try it again. There we go. Okay. Okay, so this is going to give me, this is the instructor's page. That doesn't have too much. But what you should see is along the top, assignments. Right, once you get logged in, create your account, this should take you to a page similar to this one and show you assignments. Then when you call up the assignments, you're going to see chapters on the left and then subs of various things. And you really, the only 2 that you're going to be graded on are this one called Mastery and this one called EOC, which is end of chapter problem.
So we have a bunch of like chapter 10s and 11 assignments, but we're only being graded on like 2 of them.
Right. The others
Aren't they just practice?
practice, right? You could start with Mastery, because if you go to Mastery and it goes like that, then you're good to go. Then just go to end of chapter, knock those out.
Also, that's for each chapter.
Do these give us the chance to redo them? Because I use this on one of my assignments, and it'll tell you when you collect it, it'll tell you if it's right or wrong, but it'll give you multiple chances to try them again.
Yeah, I gave you some extra chances. Yeah. Yeah, the whole point of this homework is to, it's interactive learning, where people tend to learn better when they.
Yeah, because what it'll do is it tells you if it's wrong, and then it'll give you a link, and it'll take you where in the book textbook, it'll tell you where you can read about it.
Yeah, I think it does that. This is the first time I've used it, so I'm kind of murky on some of those.
I used it for one of my classes last semester.
Was it OWL? Okay, okay, then it should do that. If it doesn't, let me know, and that means I have to go in and enable it somehow. So only those two in each chapter are the ones that are great, mastery and EOC. And they're all open. They should all be open now. They have different due dates, but they're all open at this time. So you can
work on any of them.
work at your own pace, right?
All mine have the same due date, all said 12/14.
Really? Oh, that's not right. I went to all the trouble to get
So
them.
they'll close and like we'll be able to go in and try it again after the exam.
Oh, you know what happened? I put in that due date, that's the end of the semester,
Yeah,
so
they'll
that,
say it, and then
so that you can go back and use them as a review.
Oh, okay.
So the due dates, I have to impose myself independently. These things are not gonna, the OWL itself is not going to impose a due date.
So is there only 2 papers we need to get back to you to sign?
Three. There's there's the safety, and there's the, each of the syllabus.
I think I only have 1 to
I have 2 of the safety, you just need 1 and 3.
You have that one?
do. Yeah, that's the one I brought.
Okay. How about this
I
one?
have this safety, I have this one.
Lecture.
These two.
Okay. Keep them all together.
Turn the lights back on. I already did get that other one too. What did that do with it?
Oh, it's down here. I can keep them all together because there's only 3 of them.
Yeah, I came in, I saw the roster, I was like, man, that's a
Right,
small
that's what I
class.
said.
I think, well, actually, the school's not gonna lose money on it. Because what they do is, they make my base load the classes with higher enrollment. And then the adjunct contracts they give me for the ones that only have 3 or 4 students. Which means they have to pay, they pay me less money.
So are we good to go now?
I'm pretty sure, are y'all gonna pick these up on your own, or do you want to?
I already have one.
Oh, okay, and you got one already. You want one?
No, I've got one.
Okay, good to go.
Yeah, I was about to say, I labeled mine today already, so.
Okay,
I
Well, I
didn't run
didn't
it
want
label, I
to
just
label.
need to go through and do my 105 numbered pages.
oh, yeah,
I'm kind of upset that I spent all the time numbering all those pages, and then we only used like 30 of them.
that's just evil, isn't it?
I don't know, I was like, man, I numbered all these pages and I didn't even use them. Take a picture.
I'll pay for it in the afterlife, probably. Oh, I need to stop this thing. There we go.